In this video, we're going to take a look at a legal problem called interleaving string. So given strings S1, S2, and S3, find whether S3 is formed by an interleaving of S1 and S2. So interleaving, basically what we're trying to do is we're trying to see if we can be able to form S3 if we interleaving S1, S2, right? So interleaving basically means that we take two strings and basically S and T, right, is a configuration where they're divided into non-empty substrings. And then you can see here we have an example where we have S1 and S2. If we divide them into substrings, right, or subsequence, we can be able to concatenate S1 and S2 into S3, right? So you can see here the order still stay the same, where A comes before B, right? D comes before B for this string, right? B comes before C, right? So you can see the order stays the same, but you can see here we're basically concatenate the or basically interleaving S1 and S2 and basically combine them together, form S3, right? So you can see here we have S3 string right here, and then in this case you can see we can be able to form a string like this, right? So initially you might be thinking maybe we can just use pointers, and here you can see just like a merge to linked list, right? We have a pointer here for this S1 string, and then we have a pointer for S2 string. We might have a pointer for S3 string, and what we check to do is we check to see if A is equal to A. In this case, this character is equal to this character, so we move this pointer one to the right. Okay, and then since they're equal, so we move the S3 pointer one to the right, right? So this is the S3, and this is the S1 string, this is S2 string, right? So in this case, this is another A, so we know that this character is equal to, so we move both character one to the right. And then we have a D, okay, so we move S2 string, S2 pointer, and then S3 pointer one to the right. Okay, so you can see here we have a B, and we also have a B here. So that's where the problem becomes difficult, right? Because you can see here, we cannot solve this using just two pointers, right? We can't just solve this using just like a loop through S3 and try to move our pointers across the string, right? In this case, you can see here, we can have a B here, right? In this case, there are two B's. So there are two situations. If there are two situations, in this case, there are two paths, right? Because in this case, I can take this B, right? In this case, the B from S1, right? And basically, or I can take the B from S2, and then you can see here, if I take the B from S2, then I continue to traverse the string. Then this is our S1, and this is our remaining S2, right? And then you can see here, we can also take the B from S1. You can see if we take the B from S1, we kept the B from S2, and then we continue to traverse the remaining strings for S1 and S2, right? So in this case, you can see we have two paths here, and if one of those two paths return us true, right? If one of those two paths returns true, then we know that there is a way to intervene S1 and S2, convert it into S3. And if all of them, right? If all two paths return as false, right? If all two paths return as false, then we know that there's no way for us to intervene this string, right? So in this case, if we were to perform this brute force approach, then the time complexity will be big O of 2 to the power of n, which is basically exponential, right? Worst case scenario, we have each and every single characters is equal to each other, right? So in this case, we could have a situation where each and every single character in S1 and S2, right, they're equal to each other. So in this case, we have two paths to go down to for each and every single position. So in this case, we're going to have a worst case scenario, which is big O of exponential. But in this case, what we can do instead is we can basically use caching, or in this case DP, to optimize the time complexity and try to bring the time complexity down to big O of m. M times n. M is basically the size of S1, and n is basically the size of S2. In this case, to solve this problem using dynamic programming, what we can do is first let's try to break down, or let's try to draw a recursion tree and see how we can be able to cache this, right? So you can see here we have our S3, S2, S1, so we have a smaller examples here. And in this case, we're starting from in this case, index 0 and index 0, right? This function, we basically takes two index, right? The index or the pointer for S1 and the pointer for S2. And then what we can do is we notice that the first two characters, or the first characters in both strings, they're the same, and they all equal to S3. So in this case, what we have to do is we basically have to branch off, right? So in this case, we basically have to branch off two paths here. So in this case, first, let's try to see if we take the A from S1, right? So in this case, we're taking the A from S1. So in this case, we have index 1, right? Where now the pointer is pointing to index 1, which is B, and the S2 pointer is still pointing to the index 0, right? And then in this case, you can see here, we're still dealing with this, right? So in this case, what we're going to do then is we're going to continue, right? We know that there's no B in this the next character that we have in our S3, right? So the next character is actually D, right? So in this case, our current pointer is pointing to this and then this. So there's no characters that current pointers are pointing to is equal to D. So therefore, we're backtracking, and then we're returning false. And of course, we will also have to save this in maybe some kind of like 2D array, right? So in this case, we can have a 2D array table, and then we have this is the row or this is the column, right? And then we store that this is going to be false, right? So that in this case, let's say somehow in the future we have a bigger example, and we revisit that situation again, we can be able to retrieve that in our cache, right? And now what we're going to do is that we're going to backtrack, right? We're going to backtrack to the root again, and then what we're basically going to do is we're going to take this A from S2. Okay, so now the pointer is pointed to here, and then the pointer for S1 is still pointing to that. So in this case, for this path, we're basically just going to have the S2 pointer pointing to index 1, S1 pointer is pointing to index 0, and then what we're going to do is we're basically know that the next character from S3 is D. Okay, so that's perfect. So we have the D, right? So in this case, what we're going to do is we're going to move this pointer right here, right, to a empty string, right? So now we are pointing to an empty string, but which is okay, right? We can still, if it's an empty string, we can still comparing S3 with S1, right? So what we're going to do then is we're going to do our DFS, right? So in this case, Fn, 0, and 2, right? So in this case, S2 is basically going out of bound for the pointer. So then we're going to compare the next pointer with the current pointer, right? So in this case, we have this character right here, which is A. Luckily, we have S1, the current pointer is also pointing to A. So then we're going to have our Fn, right, 1 and 2, right? So we're going to move our pointer 1 to the right. So now we have this pointer also move the 1 to the right. So now we're B, so they're all the same. So we're going to continue, right? So in this case, we have Fn, 2 and 2, right? And then we move both pointers 1 to the right, and you can see now we know that right now is basically done because you can see we're basically reached to the end, right? So this pointer right here, you can see is reached to the end, and therefore we can basically know we successfully traverse or successfully iterate through the S3, right? So in this case, what we're going to do is we're going to return true, and then we make sure we while we're returning true, right, we're going to make sure we cache the result so that we can be able to revisit it later, right? So we're going to return true, 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 all the way back to the root, and we know that this path is true, and then what we can do is that we can just return true, right? So if it's true, we don't have to traverse another path, we can basically return true right away, okay? So now let's take a look at the top-down approach in code. So you can see here, we're basically starting and we're basically converting all of those strings into a character array. And then what we're going to do then is we basically check our base case, right? So just like I mentioned before, if S1's array, if the size of S1 plus S2 does not equal to S3.length, then we just have to return false, right? We have to make sure that S1.length plus S2.length is equal to S3.length. If they don't, there's no way we can be able to intervene all the characters that we have that match with S3, right? So then what we do is we build our cache. In this case, our cache is basically S1 array.length plus 1 and S2 array.length plus 1. The reason why we do a plus 1 here is because there could be a situation where the current pointer for S1 or the current pointer of S2 is going out of bound. So in this case, we still want to continue to move the other pointer, right? If one pointer is pointing out of bound and the other pointer is not, we still want to continue to move the other pointer across the string, make sure that both pointers is pointing out of bound, that we know is true. If not, we just return false, right? And you can see here we're calling this DFS function. We're starting from 0, 0. So in this case, both pointers are starting to pointing at the first character for both strings. And then base case is that if all of them are out of bound, we can just return true, okay? And then first what we do is we check to see if it's already been cached before. If it's already been cached, we will return what we store in the cache. And then in this case, you can see if it's not null, right? In this case, you can see if it's not null, we return that. If it's null, we will continue to compute it and return what we have in our, and save it onto our cache and return what we have in our cache. So we can see here we have this character of unknown. Just like the question is mentioning, we want to be able to do this using, these characters are all in lowercase in English letters, right? So what we can do is that we can have this character of unknown. Basically, what we're trying to do here is that if PS1, right, the pointer for S1 is out of bound, then we can just put unknown here. If the basically once the code gets to here, we know that either one of the pointer is out of bound or none of them is out of bound, right? Because we already can do this condition check to see if all of them is out of bound, we can just return true. So then by the time when the code gets to here, we know that one of the pointer is out of bound or none of those pointers are out of bound. So what we do is that if it's out of bound, we assign the S1 character to be unknown. If S2 character is out of bound, we can assign S2 character to be unknown, or we're going to assign the current character in S2 string or S1 string, right? And then you can see here for the index for S3 character is basically the sum for the S1 pointer plus the S2 pointer, right? And you can see here when I draw this, right? If I want to know if I'm at this position, right? Like 0 and 1, so 0 and 1, right? Or at the end of the position, right? In this case, if I want to know the index, is basically those two sum. In this case, 2 plus 2 is 4, which we know that the S3 current index, right? Current pointer is pointing to 0, 1, 2, 3, 4, right? Which is out of bound, right? We know that that's out of bound, and we can be able to use the current indexes, right? Those two pointers sum to get the current pointer for S3 that we're pointing at. So we don't need a global variable to store the pointer, right, for S3. So in this case, you can see here, we can basically just calculate that and then get the S3 character. We check to see if both characters are equal to each other and both characters does equal to S3 character. If they do, we basically doing our DFS for both directions, right? So either we take the A from S1 or we take the A from S2, right? If one of those paths returns true, then we know that the current position is true, and then we save it onto our cache, right? However, though, if S1 character, right, the current pointer for S1 is equal to S3 character, but S2 character does not equal to S3, then what we can do is we can continue to move our pointer for the S1 path, right? We can continue to branch and go only this one path because we know that S2 character does not equal to S3 character, right? However, though, if S2 character is equal to S3 character, then we can do the same thing, but we're going the opposite path where we're basically just continue to move the S2 pointer one to the right, right? However, though, if none of them is equal to S3, right, character, if S1 character and S2 character doesn't equal to S3 character, we're going to assign the current position to false. And at the end, we're basically return the result of the computed value, right? So basically, this is how we solve this problem in a top-down approach. But before we jump into the top-down, bottom-up approach, I want to talk about the time complexity here. So the time complexity, as we know, just like I mentioned before, is going to be m times n, right? M is basically the size of S1, and n is basically the size of S2. So, but the space complexity is also going to be big O of m times n, because you can see here we have a cache array, and this this 2D cache array basically has m times n, right? It basically has the size of m times n. So now let's take a look at the bottom-up approach. So now let's take a look at the bottom-up approach. So the bottom-up approach, you can see here we have our DP table, right? This is our DP table, and for the columns we have our S1, and then for our rows we have our S2, right? So same input, we have our S1, S2, and S3, right? And then you can see here we have our index label above, so it's basically a 2 or 3 by 3 grid, right? So you can see here for our last row and last column, right, it's basically an empty string. So you can see here we have an empty string, and this is our empty string column, and this is our empty string row, right? So in this case, what I'm going to do is I'm going to show you, I'm walking through from cell by cell, step by step, and then basically you can see we're starting from the bottom right, working our way up to the top left, right? So in this case, for our bottom right position, we know that if we have a situation where they're all out of bounds, right? These 2 pointers, they're all out of bounds, we can basically set to true, right? If they're all out of bounds, we can just set to true. Okay, so what we're gonna do then is we're gonna move to the next adjacent cell, which is go from right to left down to top, right? So in this case, the next element is here, and right now basically what's the situation here is that we know that the maybe let me just label this. So we know that here the columns here is S1, the rows here is S2, right? It doesn't really matter the order, but you can see here right now the columns is S1, rows is S2. So for S1, basically you can see here at this position, S1 has a D, okay, and then S2 here has a space. So in this case, what's their index? So the index here is a 2, index here is a 1, 2 plus 1, right? 2 plus 1 in this case is a 3. So 3, index 3 in S3 is 0, 1, 2, 3. So which is the last character, which is a B. So in this case, one is an empty string and the other one is a D. In this case, they don't equal to B, right? So therefore, we put this position to false, right? So you can see here, we're going from the bottom, from the base case, right? From the bottom of our recursion tree, working our way up. And this is basically a situation we're saying is like if S1 right now, the current pointer is pointing to the last character, index 1, and then the current character for the current pointer for S2 is pointing to out of bound, then the result should give us false, right? So then what we're going to do is we're going to continue. So the next character, we have 0 plus 2, right? In this case, A and an empty string, right? So in this case, S1 is A, S2 is an empty string or out of bound. So in this case, what we know is that 2, right? The index is 2 plus 0, which is 0, 1, 2, which is an A, which is matched with, you know, this character right here, right? In this case, if it matched this character right here, what we want to know is, does it match with the remaining characters, right? So what's happening right now is S1 right now, the current pointer is pointing to A, but we still have AD, right, left, right? So in this case, S2 pointer is already out of bound. S1 pointer is pointing to A, and we still have a D left. So we want to know if the remaining substrings match with the remaining substrings of S3, right? In this case, it doesn't, because you can see here the neighbor cells already computed, and it's gave us false. So therefore, this position will give us false, right? We're using the pre-computed value to compute the current cell. Okay, so then we're gonna go back to the next row, the above row, and then we're going from right to left, right? So we're using the pre-computed value to compute whatever we're computing. And you can see here for the index for the S1 pointer is basically 2, and then for the index for the S2 pointer is basically 1, right? We're at this cell right here. And then in this case, 1 plus 2 is 3, so 0, 1, 2, 3 is a B. So we know that this character is a B, this is an empty string, so one of them match. In this case, we're basically returning true, right? So then what we're gonna do then is we're gonna move on to the next cell. In this case, is this one right here. And then we know that this index is 1, this index is 1. Sum of 1 plus 1 is 2, 0, 1, 2. In this case is an A, right? In this case, none of them equals to A, so we're gonna put F here. We're gonna put false, right? and then we don't have to check the pre-computed value because in this case B and D doesn't equal to A, right? So then we move on to the next cell. In this case we have B and A, right? In this case B and A, in this case S1 right now, S1 pointer is equal to A, S2 pointer is equal to B, and their index is 0, 1, right? In this case is 1, so 0, 1, which is a D. AB doesn't equal to D, so in this case we set this position to false, right? So then we move on to the above row, and then now you can see this is where the magic happens. You can see here that this right here is basically an empty string, right? So right now S1 pointer is empty string, S2 pointer right now is pointing to A, okay? Or actually AB, but we're pointing to the first element, right? So in this case, what's going to happen then is we're going to check, right? So this is index, so 2 plus 0 is 2, right? 0, 1, 2, which is A. So in this case, A is matched with this A, so we're going to set this position to true. And then we move up to this D right here. So we have a D here, okay? So in this case, 0 plus 1, which is index 1, so 0, 1, which is a D, right? So this D right here, you can see, is actually equal to this D. So we can put a true here, right? But what we want to know is we want to know if the remaining substring for, in this case, the remaining substrings is equal to true, right? So you can see here that the below cell, which is a F, right? In this case, if I keep this D and I remove this A, it will give us false, right? This path is a false. We already know that, we already cached that. However, though, if we remove this D and then we continue to do our DFS, we know that this path is true because we come from that, right? We already compute that, it's already true, right? And which makes sense because you can see here, after we remove AD, we just have AB, and in this case it matched with S3, right? So then we continue, right? In this case, the last cell that we have, the top left, in this case we have AD, right? This is our core question. You can see here, the index is 0, right? So index 0 in S3. So what we're basically trying to do here is that we're basically trying to see if A is equal to A. In this case it does. Then we have two paths, right? This path is basically we're taking A out from S2. This path is we basically take A from S1, which we will have D and AB left, right? So in this case, one of those two paths is actually true, so therefore this position is true, okay? And then at the end you can see here, this is what we are looking for, which is the first element in the 2D array, right? So now let's take a look at the code. So code is very simple. We basically convert them into a character array, have our Boolean 2D array that represents our cache, +1 here because, like I mentioned before, we need a space, we need extra row and extra column, represents space, okay? And then what we do is we do our base case to see if the size of S1, S2 is the same. If not, we return false. Or sorry, the size of S1 plus S2 is the same as S3. If not, we just return false, right? So then what we're gonna do is we're gonna make the last element that we have in our cache, which is here, to true. And then what we're gonna do is we're gonna loop through starting from this cell right here all the way to the top left, right? Maybe let me do this side by side. So you can see here we're looping through from the last element to the first element in the array, and then in this case, because we already set the first element to true, so in this case if it's true we just continue, and then what we're going to do is we're going to compute the index for S3 PS, or the position or the pointer for S3, right, which is basically pointer for S1 plus pointer for S2. And then just like how we did it in the top-down approach, right, we basically set the current character to unknown if the current pointer is out of bound, right? So in this case, this is the condition, right? If character 1, first character is equal to, or S1 character is equal to S3 character, and S1 character is equal to S2 character, then we take two paths, right? We take either the bottom position or the right position, right? The pre-computed value, or if S1 character is equal to S3 character, we're just going to take the adjacent character, right? The adjacent cache position or cached value. If S2 character is equal to S3 character, then we're going to take the cache value for the adjacent character, right? In this case, the JSON element, right, or the bottom position, the bottom cache value, and this one is the adjacent or the right cache value, right? If none of them is satisfied, then we can just set the current position to false, or we don't even have to do this because by default, all the elements in cache is false, right? And at the end, we're basically just taking the first element that we have in a 2D array, okay? So you can see here, this is our top-down approach, and then the time complexity for this algorithm is basically also going to be big O of m times n, where m is basically size of S1, and then n is basically the size of S2, right? But in this case, how can we be able to optimize the space complexity? So the other way we can do this is basically we can use just one directional array, right? Or in this case, a one directional array that has a size of m plus n, right? So m plus n, or basically the size of S3, or so length of S3, right? So that will be our space complexity. What we can do instead is we basically can just use one directional array to cache this result. And you can see here that for our empty string, right, in this case, we can walk through here again. So you can see if it's empty string, we're going to have true here. And then what we're going to do is that we're going to move to the next character. We're still iterating through m times n, but the space complexity can be a lot more better, right? We can just use a one directional array. And then you can see here, once we get it here, right? Once we get it here, let me just set this to empty here for now. So once we get to here, right? Once we iterate through, right? We go from the bottom right to the top left. The first element in this case is 1 and 2, right? In this case, 1 plus 2 is 3. In this case, 3, 0, 1, 2, 3. In this case, last character does not equal to D. So we set this position to false, right? We know that this position right here is false because in this case, B does not equal to D, right? And then we move to here. In this case, it's 2, 0, 1, 2, A. In this case, A does equal to this. And then we check to see if the remaining characters, right, the remaining substrings of S1 is equal to, can be intervened with S3. In this case, we cannot because it's false here, so we're going to set false here. And then what we're going to do is we're going to move on to here, right here. In this case, 2 plus 1 is 3. So in this case, the last character is B, and this character is B. So what we can do is we can set this to true. And then once we iterate to here, in this case, we have D and B, right? D and B in this case has a total index of 2. So 0, 1, 2, which is A. A does not equal to D or B, so therefore we set this to false. Okay, so we continue to set this to false. Here, same thing. In this case, we're basically have A and B. A and B has an index of 1, so 0, 1, which is D. So in this case, we should set this to false as well, because AB does not equal D, right? And then we also move on to the last, or the first row, right? In this case, we have empty string here, so 2 plus 0, which is 2, 0, 1, 2. In this case, is A. A is equal to A, right? So therefore, in this case, what we're basically just going to do is we're just going to set that element, right? In this case, is index 2, 0, 1, 2, which is set to true, right? Because we know that this position is true, right? So then we continue, and then we have AD. AD in this case has an index of 1 plus 0, which is 1, so 0, 1, which is D. D is equal to D, right? And then we check, in this case, the remaining substrings for S1. In this case, the remaining substrings S1 is true, right? So in this case, we can just set this to true. And then we continue. So as you can see that the time complexity is still big O of m times n, but the space complexity is big O of m plus n, right? And there's also other ways we can optimize this, or different ways we can cache this using just like size of n, but I'm not going to go through that. So you know we can be able to further optimize the space complexity here to optimize our caching, right? So there you have it, and thank you for watching.